Afternoon, my name is Stan Kulikowski. I'm a product development manager for Fenner Precision, and we wanted to put a little presentation together today to let you know about some things that we do in precision belting, some new developments, new materials, and the way we've encountered some common problems in applications. So some of the new things that we've got going here, recently we've produced what we believe to be one of the world's smallest belts ever produced. So I'll give you a little bit of an overview on that. We've done a lot on the extremes of both low friction and high friction belting for different applications. We've done a lot of work recently in vacuum transfer, very special applications for media handling, using vacuum to draw belts, draw media down to the belt and transport it. We've got a lot of belts going into some harsh chemical environments. Talk a little bit about how urethane works in those environments and how we're able to formulate around some of those issues. And then the last thing I'm going to hit on is some new regulations coming in Europe for REACH and how that affects polyurethane and possibly some of the parts that you might have going into Europe. So the smallest belt that we've done right now is 53 millimeters in circumference. And you can see up here, how that relates to a penny. We've got some samples around here that you can take a look at for that belt. It barely fits on your pinky. So why would you want to use something like this? I mean, typically, you get into that small of an application, people think of just using a gear train. Well, you still have to fit 3 gears in that space if you want to get 2 shafts to rotate in the same direction. So you've still got 3 components, and typically, gears are still going to have some noise associated with them with clatter. The belt drive gets rid of a lot of that issue. We get all the other benefits out of belts if you're actually carrying the media across a gap with this belt. The urethane formulations are non-marking. Typical applications here are media transfer in medical equipment, printing equipment, things of that nature. We've done a lot of work recently on some low friction belting. A lot of our customers are putting these belts into applications where they're running through a channel, and they've got stationary components that the belt needs to run against. And of course, this builds up heat, increases the size of the motors that would be required to generate the torque to keep the belt moving. So we've come up with a way of blending lubricants into the urethane formulation that will reduce the friction to the point where this belt will run continuously without building up heat, without creating a lot of wear and particulate matter that gets trapped into the drive. It's reducing the noise, and at least in the latest applications that we've seen, it's been a very cost-effective solution versus looking at trying to add some sort of powdered lubricant into the system to accomplish the same goal. On the other extreme, we can formulate urethanes to go into these belting products that have very high coefficients of friction. This particular belt here is used in a high volume mail sorting application. So we're carrying a lot of envelopes. These envelopes come through the system, they get weighed, the postage gets assigned to them, they get return address labels printed right on the envelope, and it gets spit out the other side at a very, very fast rate. So the urethane that was used was specially formulated to increase the friction against paper. So this particular belt, a 1.5 COF on paper, which is, quite high for typical urethane formulations in this same hardness range, would be around a 0.8. So we're, nearly double. Other applications that could use something like this would be in, credit card printers, ATM machines, anything that's carrying some sort of potentially paper media. The second interesting thing about this particular belt is on the back side of the belt is ground, and there are reasons for that. The grinding actually gives a place for debris to hide. So, I'll talk about it a little bit later as well, paper tends to be very dirty. You don't want a very smooth surface on the back side of the belt, otherwise the debris that's on the paper will actually start to build up, and then you start to reduce your friction. This belt here with a ground surface actually doesn't allow the debris to build up on the back side of the belt, maintains a consistent friction over the life of the belt. The unique thing about being able to injection mold polyurethane to make these belts is that we can mold features right into the product, just like you would in more standard injection molding. On non-polyurethane belts, these features tend to be added as a secondary operation. So we can mold these lugs and vacuum channels like you see in the top picture and the picture on the lower left. All those features are molded right into the part. There's no secondary operation to them. Basically, as long as we can split the mold apart, we can put some sort of feature in there. The second way people are starting to look at vacuum transfer is punching holes that you see in the lower right. And we can punch holes, we can drill holes. There's various ways of putting these ports into the belt that would allow vacuum to be drawn and actually take the media and suck it down to the belt to make sure that you don't have any kind of slippage between the media and the belt as the media is carried through the application. Urethane's well known as a pretty inert material. We've been able to specially formulate different urethane polymers that can be used in high chlorine contents in swimming pools. We've had a lot of applications where we've actually displaced chain. The chain tends to be less efficient than the belt. We've been able to put formulations of urethane in there. It will be submerged in the water throughout the life. You can see the picture of the swimming pool cleaner there running along the bottom of the pool. We don't have any issues with the urethane swelling. It stays in its same shape as it was when it's molded, and actually performs very well. Lasts multiple seasons of cleaning a swimming pool before the belts would have to be replaced. And as I mentioned earlier about paper being very abrasive and very dirty, I've seen a lot of belts come back from the field in dollar bill changers that are in ATM machines or vending machines. And when these belts start to slip, they usually have some sort of glaze or dirt built up on the back. And if you scrape that off and you look at the surface of the belt is smooth. So we've developed grinding processes in addition to the special urethane formulations that will, not allow the dust to build up. It kind of creates crevices for that debris to hide and not allow it to affect how the belt carries the media through the rest of the application. And the last point to hit on is REACH. REACH is a new regulation that's coming from Europe. Some of you may have heard about it. It's affecting a lot of the plastics industry in additives that are being used within not only polyurethane formulations, but also within PVC and in other areas. A lot of these additives have been put on what's known as a substance of very high concern list. So what we have decided to do as part of Fenner is actually, instead of trying to register products and get our products into Europe sort of around the regulation, we've taken the stand that we're going to get these substances of very high concern out of the formulation altogether. So we've worked with our suppliers to come up with alternative additives that we've been using in the belting formulations, either as softening agents, plasticizers, things like that, that would be REACH compliant materials. And we've been able to figure out ways to process those, and we're working with our customers to make sure that they're compliant with the REACH regulations, as a lot of their products that they end up supplying go into Europe. And we're, as long as they're successful in supplying the products to Europe, we'll be successful in supplying the products to them. So with that, we'll open up the floor if there's any questions.
How do you handle belt strength in extreme cold temperature?
Extreme cold, define extreme.
Minus 40 centigrade?
Minus 40 is about the lower limit. You start to see, I mean, with any urethane, any polyurethane formulation, it's going to start to stiffen probably around, it'll start to stiffen probably around minus 20. You can, depending on what efficiencies you're looking for, you can push the envelope to minus 40, but I certainly wouldn't be going much below that. There are things that can be done in the backbone of the polymer that you probably push that envelope to about minus 50. We haven't had the need to go that way yet, but I know that there's technology out there to do that. Well, thank you very much.